What's up, what's up? Welcome back. Today we're working on my operating system. So it's like a x86 operating system. It's, for fun, right? And it's got some form of resemblance of an OS at this point. So it boots, it has like memory allocation, it has a concurrency through Rust's async await model. We can log to serial, and previously we could log to the monitor, but we've replaced that with some sort of like game that we're running instead. We have like unit testing, we have the RTC or clock support, we have PCI and Ethernet card support, specifically one Ethernet card support. And through that Ethernet card, we can kind of like do address resolution, UDP, TCP. We've proven a web server at this point. We've written a game using some sort of like shitty graphics stuff. And we've got like keyboard input enough that we can like run a little game demo. Let's just make sure that I'm in a clean state. And if I like run a quick little demo here, hold on, let me get my environment set up correctly. Right, like we have logging here, we have a little brick breaker demo. What else? If we try to like connect to it, we have like netcat to a specific address and port. And if I say like hello, we see that data come in and we send it back. Great. What we're working on is we're currently working towards multi-core support. So the OS kind of assumes single thread. So if I like, let's see, do I have an editor open? I do. If I look for like impulse sync, maybe sync 4. Okay, so there are like cases where we have like something that has an unsafe thing in it, and we implement sync for it, which means like it tells Rust, hey, you can put this in a context where multiple threads can access it. And we're just kind of ignoring the fact that this isn't actually sync, because our OS only runs on one core, so things that would normally be unsafe are totally safe for us. But if we enable multiple cores, all of a sudden that becomes a problem. So we've been working towards that. And yesterday we were looking at this, like, we were fixing one section of the code, and we realized that using a B tree set from Rust's collection library just hard crashes the OS. And we looked at it a little bit, and we didn't get very far. And so today I kind of want to look at like why that is and see if we can fix it. And probably that will take long enough that we'll just call it there. If we can get to the point where the B tree sets are working right, we'll probably be pretty happy. If that goes really quick, then we'll probably just continue on with the fixing up our like multi-core stuff, like getting prepared for it. Okay, so that's intro done. And let's start looking at where we were yesterday. So I think I had a branch here, B tree lockup. And if I go to like my main, I have a demo in here. And in this demo, all I'm doing is I disable interrupts, I print something, and then I try to use a B tree set, right? I just like allocate it and insert some numbers into it. And I print between them just to kind of like get a feel for what's happening. If I run this, sorry, let's run in debug mode. And I have GDB open. So what happens is I'm running this in a virtual machine, and QEMU has this like pretty nifty support for what is it, -s maybe, whitespace -s. Where is it? There's an option basically that says like, hey, let me I want to try one more search first. We'll search for whitespace -s whitespace again. No, whitespace -s whitespace. There we go. Do not start CPU with startups. It's the other one. It's -s or whitespace -s whitespace. Alright, I'm not finding it. Anyways, it has like this nifty feature that lets you set up like a GDB server, and since QEMU knows that it's running my kernel, it can provide like debugging information back to GDB And that lets us like debug the kernel on initialization and stuff. So that's why nothing's happening right now. It just says like nothing started. It's because we haven't connected GDB yet. So I'm gonna start GDB, which is just like the Linux debugger, whatever. GCC's debugger, GNU's debugger, I guess is the right word. GNU debug, GDB. And I'm gonna connect to the QEMU instance. And I'm just gonna hit continue. And here we see like, we started like allocating some stuff. We have some logs in here from last stream. And we have like some interrupts logs, but then we kind of like get stuck. It just starts hanging. And so what I think we could do is if I connect GDB and just breakpoint, we can kind of get a clue at like what the call stack looks like. So here, what are we looking at? We go into the interrupt handler and we're trying to print out something. Right, we can't see our backtrace from the non-interrupt context at this point. I think. Oh, yeah, I'm not sure. There's like the backtrace stops here, but probably we could like restore it, if we were a little tricky. But it's okay. We don't really need that. And we're trying to write our serial into like a log to serial, and we're hitting a bug where we're colliding with the fact that the serial is already borrowed. So let's take a look at that. Let me get my development environment open. One sec. Okay. Oops, I whistled and my dog just got really excited. That was stupid. Oops. Okay. So I think where this is this at doesn't have the file and line, but I think we're at main rs. Oh, 114. Here we go. Here, so what we have is we have this like write implementation for our serial device that requires a mutable reference. So we use like a ref cell, which is Rust's way of saying like, hey, I'm gonna like modify this thing in there, but I can only modify one at a time, and I'll check at runtime that I'm the only one. And then what happens is like, since that's like a runtime check, we try to print. We panic. It says like, "Hey, I'm supposed to be the only writer." And then in panic, we print again. And I think it's just like hard looping on this forever. So it will eventually hit a stack overflow, right? We'll get so deep into the stack that every allocation, we'll allocate a little more space every time, and we'll just like overflow and get to the, like run out of room. So I think what we can do here is let's look at the serial implementation. Does it really need a mutable reference? Kind of. He's saying that he needs a mutable reference because he wants to write to the serial port, and only one person is allowed to write to the serial port. The serial port has like a single writer. It has like a mutable requirement because we didn't want like multiple people to write to the same IO port and clobber. However, we can say in our case that we're content with. We could argue that if multiple people try to write a string to the serial output, they'll just like overlap with each other, and that's okay. I'm okay with that. So what I'm going to do is I'm going to make these immutable and try to recompile, and somewhere is going to tell me that that's not fucking allowed, right? Because serial IO is a reference, but it needs a mutable reference. And I would think that what we can just do is we'd say unsafe cell, like this, which is like Rust's way of saying like, hey, screw you, I'm going to do this anyways, and I'll just be very careful to make sure that I don't break your rules. So that's, I think I use core cell unsafe cell. Now, this actually does break rules though, which kind of sucks. Maybe. Right, because like the IO range does expect that it's the only writer. But all this guy does is like call some manual inline assemblies. I think it's probably okay. Yeah, I think it's probably fine. This is like a little sketchy, but let's just for now try it and see what happens. So we'll say get Oh, we also kind of have a problem where... Oh no, this is fine. This is fine. Sorry. I was gonna say that if we're doing something with this thing that isn't writing to the data port, then like we might run into trouble. But that's okay. I'm also seeing that we have a like hot loop on if the serial port is ready to accept data, and so this actually does that actually does cause a problem. Shit. So maybe what I'll do, what I was gonna say is like I could try mutex, right? I could wrap this in a mutex, but then if I print from an interrupt, the mutex might be locked, or we might deadlock, so we can't do that either. So I guess what we'll do instead, how can we do this? So it would be nice if we could make this safe in a way that we always get something out, right? I guess if there's people racing and they write at the same time, and transmit is not ready, they're going to write like only one of the two characters that are trying to be written from the two different threads will be written at a time. And that sucks. In our case, we're like in an interrupt, so we know that there isn't going to be somebody else trying at the same time. So it's like, is transmit ready is like sane. But I wonder if you could have like is transmit ready? Could maybe go through some sort of atomic and be like, you check transmit ready, and then you like acquire some lock that says you're the one that's going to be transmitting, and then you release the lock. But then we're in the same state where interrupts could get blocked by non-interrupt code forever because the non-interrupt code will stop running. I guess you could check, is transmit ready? Yeah, I don't have a good answer. I don't have a good answer to this. So I guess what I'll do instead is I'll just should I just let us clobber each other? That's like a better answer, right? So if I panic in my interrupt handler, I want that log. That log is like extremely important to me. More important than threads clobbering the standard output. We will have to solve this at some point anyways later. I wonder, maybe we make like a special write context for interrupts that's different than like the normal write context. All of this to say, I've thought it through, and I am just going to make this. I'm just going to violate the rules here. I'm going to use an unsafe cell. Fuck it. So that's use core cell unsafe cell. Here we say get. Here we say get, and we dereference. This is serial IO is now an unsafe cell. New this guy. Like this. And these guys don't take mutable references anymore. Is that it? Cargo check. I fucked up my syntax here, so that explains why nothing was yelling at me. We need to write unsafe here. Cargo check. Okay, cool. Now if we cargo run again, oops, we're rerunning in this one. And we connect our debugger. And we continue. And breakpoint again. What do we have here? So this looks like a different backtrace. And this looks like maybe the more problematic backtrace that is actually maybe causing the problem. So I'm seeing like a stack of mmoves, which is very odd. And I'm seeing like it alternating between core intrinsics copy and memmove. So this kind of makes me think that my memmove implementation is fucking broken. Just a guess. So this is in libc. So what happens here is there are like Rust core functions that reference like the C standard library function. So if you look up like man mem copy, for example, I have an implementation of memcopy that's like really fucking stupid. He just like iterates over all the bytes and he assigns them like this, right? And this is like a function that POSIX or C maybe get like promises that will exist. And it just says like copies n bytes from source to dest. Great. So what happens is when I call like Rust standard library code, they might try to use memcopy, and since we don't have like libc because we're writing our own OS, that might like there's going to be an undefined symbol. So what we do is we like define the symbols that Rust is trying to use, and we just like implement them ourselves, like naively for now. Maybe in the future we'll try to like make like an uber optimized version, but for now we're just saying like, we'll just do anything that like will give the right answer, even if it's fucking slow. And what I tried to do was I tried to implement memmove as a function of memcopy, but I actually did something stupid where I think what happens is when they call core intrinsics copy, that internally compiles to a memmove, and we just like recurse forever. So I think probably if I replace this copy with a memcopy, which is dest source end, dest copy end. So what is memmove? Let's back up a second. Memmove is just like we copy bytes from source to dest, but the memory areas may overlap. So copying takes place as though the bytes in source are first copied into a temporary array that does not overlap. So we just copy to the temporary array unconditionally and then do the mem copy. Great. So here we need to take the vector that we've created and we say as pointer probably. Yeah, that seems right. Returns a raw pointer to the vector's buffer. Great. And let's see if that does anything interesting. Oops, I didn't want to kill GDB actually. I wanted to cargo run. And here I wanted to reload our kernel. So file target debug GDB, and then oopsie, it's not GDB, kernel. And then what do? I say I'm blanking. Oh, target remote localhost 124. And this just says like I want to connect to QEMU. And we'll hit continue. And we seem to have crashed again, so let's see what we're crashing on now. Oopsies. This is like nothing interesting. So why are we crashing? Let's try to roll the dice again, maybe. Oopsies. So let's try to get like a quicker breakpoint in there. Oh, okay, so this time I think it actually might have worked. Yeah, we don't see any crashes there, so that's good. Let's try again. So we say target remote localhost 154. See. Okay. Here we go. We're panicking again. So why are we panicking this time? Oh, oops. I made a mistake. I never fixed that. When we tried to fix the serial printing bug, we never actually fixed it. Because we made the serial writer allow use from multiple contexts without mutable reference, but we never fixed the attempt that we tried to, we never fixed the fact that we attempt to get a mutable reference. So let's look at that. So it's in main. And in main, we have this ref cell serial. And we'll just delete that ref cell. So we go ref cell serial. And we delete the things around it. Oopsies. There we go. and we don't do this borrow mute anymore. And what does he like here? Here we construct with a ref cell. We don't need that anymore. Cargo run. And we target remote localhost 154. And there, that one worked. We continue. Yeah, that looks like it's like kind of consistently starting now. So I think we might have potentially fixed the crash. The crash might have just been that stack overflow from memmove. That might have been the only real problem. In which case, that's cool. So let me just close all these editors. And let's go back to main and look at our demo. Hey yo, what's up? Let's uncomment this stuff and try to go back to the actual thing we were trying to do last stream, which was fix our sleep implementation. So not a whole lot. How are you? Pretty good, pretty good. So our latest sleep implementation, what it does is it's kind of split the responsibility into a few segments. One is that we have like these like multiple threads all like requesting sleeps, and they will all like go into this single thread. Here, we'll go like this. Thread's the wrong word here, but that's okay. So let's say we have like multiple chords. 1, 2, 3. All of these guys will like send their sleep requests to this guy over here. So they go like, sleep please, z, sleep time. Then there's like this like chunk of memory. And he is like the list of sleeps. And so this thread will like update this memory because we only want like one thread to be able to update him. And then when we interrupt, we will also, from our interrupts handler over here, say ISR. In our interrupt, he will also access this memory. And so like the reason that we split it up this way is this way we have like two chunks of memory. We have like this chunk of memory that is being used for the requests. And he can be like mutex locked. But this guy cannot be mutex locked because the interrupt, like if the mutex is locked when the interrupt is triggered, then the mutex will never unlock. So we kind of like dispatch to this case where this guy knows that he was the only guy accessing him unless there's an interrupt running. So he just disables interrupts when he modifies them. And these guys can lock the mutex when they request these sleeps. I'll probably change this again later. But anyways, that's where we're at right now. And so like what we did was we made this guy btree. And the reason we did that was because we needed like a sorted list of sleep times, or wake up times, I should say. Because before we would just stick them in there and we would check on every tick if there was a time for us to wake up at. But now we might insert a wake up time like too far into the past, right? Like we might say like, hey, I want to wake up in like 2 milliseconds. And then we might not actually like do this migration from here to here until 4 milliseconds. And so we'll miss the spot. So we need like a sorted list to say like, oh, are there any that have already happened? And so that's where this btree set comes in. And so what we're trying to say is if we can sleep sanely now after these changes, then our btree set stuff is fixed, which is nice. So let's cargo run. And I guess we don't really need the debugger. So let's take out these -s, but maybe actually we should put these behind an environment variable because they're kind of nice. So we'll say GDB is equal to GDB, else it's equal to 0. And then we can say here we'll replace dump net with GDB. And we'll GDB work. This is just GDB. Here we go. And if we have GDB, we have -s. I'm amazed about you running your own mutexes. It's actually, well, okay, so first of all, I don't know if they work, right? I just kind of like pulled it up my ass and tried to like just reasoned about it. But also, they're not that complex actually. If you look at all this guy's really doing is he's wrapping an atomic, and he's just saying like, hey, if the count is 1, I'm good to go. Or I'm sorry, if the count is 1, I can't lock. And if the count is 0, I can lock. And all he's doing is doing like an atomic check of that number. And so we're just making sure that only one person ever gets that number. And that's literally that's it, right? Because we're kind of like we're leveraging some because of like Rust's polling mechanism. We don't have to do the hard part, I think. And the hard part is that like in normal multi-threaded code, when you lock a mutex, you would say to the operating system like, hey, I'm blocked. And the operating system would then like preempt your thread and schedule a different thread, and then like come back to your thread when it thinks that the mutex is unlockable. But we don't have to deal with scheduling because everything's just using Rust async. And so all we have to do is be like, nope, not ready. And then like later Rust will schedule us, which is kind of nice. So yeah, it's what we have implemented is not crazy, but I'm sure that it could be better. Okay, sorry. So, what was I doing? I was adding support to the script to use GDB in general, so we'll just say GDB command here. And now if I run this, my cargo run with the GDB environment variable set, then it will start in that mode, which is kind of nice. Okay, so let's cargo run, and we'll see if like I get something sane. So I don't. That's interesting. I'm like crashing again. So I thought I'd fixed all the bugs, but it looks like I had not. So let's type in GDB equals 1 here. And that's kind of nice. We'll target remote, we'll hit continue, and we'll look at the crash and we'll backtrace. Interesting that there's no backtrace there. Corrupt stack. So that sounds like maybe there's some sort of overflow again. Maybe we have to get a little careful. Maybe we have to get pretty quick with it. With our like interrupt. So let's try again. Hit continue, hit break, backtrace. Yeah, something's wrong. So it could be that we're hitting some interrupt that we don't want. It could be that like all of these prints in our allocator are maybe slowing things down to the point where they're causing problems, where like our interrupts aren't being serviced fast enough. It could be that like logging every single received interrupt is slowing down our interrupt handler to the point where something is not working correctly, where we're getting like preempted by ourselves when we're not supposed to. So let's just delete this log from the interrupt handler and see if that helps us at all. So I'm pretty suspect of that. That's not it. Let's delete these logs from the allocator too, just in case. Because I just want to get a feel. Okay. So there was some form of like, maybe things were going too slow, our allocator was too slow, and that was causing interrupts to be a problem. So there's a bug somewhere where if we don't service fast enough, we'll crash. But I guess maybe that's reasonable. Okay, so this game is running okay. What if I try to like use this netcat? That's not working. Probably because in debug mode, we run just so fucking slow that we never actually sleep in our game loop. Right? Our game's probably like too quick. You'd probably be better off using some static memory and interrupt anyway. For what? Oh, if I'm allocating and that's too slow? Yeah, that's a good point. I actually don't know if I'm allocating in here at all. Let's see, what am I doing? I am looking at my handlers. That's not an allocation. Doing some like pick stuff. Yeah, I don't have maybe that must not be it because I don't really see. Oh, but it could be that in one of my allocator, like in my interrupt handlers, I have like a registration function, and in any of those I might be allocating. That wouldn't shock me. yeah, it's possible. Anyways, let's go. Let's see. Where was I just debugging? Oh, the game loop was running too slow in debug mode to the point where I was never registering sleep, so we're not actually testing the new code. So let's look at this. Let's see. So in our game loop, let's just stop rendering because we know it's fucking slow in debug. What would be nice if we could like force optimizations on in certain points in here that we know are slow. But for now, I'm just gonna say don't actually run the game. Okay, so I guess maybe what I want to do here is instead I just want to like print line hello, or maybe I'll info log it. Right, just to say that like we want to print hello every maybe 30 milliseconds is too slow now, so we'll do this every like 1 second. Just to prove that it's running. Okay, so we're getting our game loop is like logging hello, and if I try to connect with Netcat, the rest of our OS is still like being responsive. So that's like a really good indication that the new version of the sleep function is like working correctly, and that our yeah, we're not like Stack Overflowing or anything anymore, so it's just pretty nice. Let's run in release mode and see if that does it. So here, okay, something bad happened. That's good. Oh, well, not good, but it means that there's more to look at. So specifically, it's after I receive a TCP packet in release mode, we lock up. So let's start looking at that. What have we done so far? We've fixed tree set crashes, maybe, which required like an memmove fix and some print line removal and some ref cell removal. And this was done by like 32 minutes-ish. Before 32 minutes. Okay. So let's get compiling in release mode. Sorry, what we're looking at now also is debugging lockup in release mode. Okay. So let's get the debug symbols on in release. I think there's a way to do this. Rust debug symbols release. Because I already know, I've done this before, where if I like try to run in release with GDB, and I say file target release kernel, it says like there are no debugging symbols because if you're optimizing your binary, you might want to like reduce the size of it to make sure that like it like runs faster, and also just because like you don't want to like ship extra crap that you don't want. So debugging symbols are usually turned off by default, but we want them here. So I think that you can just set the profile release. You can just set debug equals true, which tells it that it wants debug symbols. So if I just edit cargo toml here, and then I say, I think it was, what was it, profile.release? Yeah, profile release, set debug to true. Now if I cargo build release, we should see, yeah, everything's recompiling because everything needs to inject its debug symbols now. Great. Wait a second. Have a sip of coffee. Okay, so that built. So let's try running with GDB again, and we'll reload the release binary. So there, he no longer says no debugging symbols found, so he's happy. And let's just hit continue. Or sorry, we can't continue. We have to connect to the target. So target remote localhost 154. We hit continue. Everything runs happy, and then I send him something. I think maybe I have to connect first. Let's see what's happening here. Oh, we're back in a little memmove loop. Okay. So what's happening here? We've got another one. So we're probably just in the same, we probably have the same bug that we had before. just like a very slightly different version of it. So before we were using, let's see if we have this in here somewhere. It must be in our diff. Before, we were using like a Rust standard library function to do a mem copy, and that was like ending up actually optimizing to a memmove, and then we were like going down the stack forever, just like calling ourselves, recursing. We're probably just in the same bug here, where if we call core slice from raw parts to vec, so this is saying like, hey, I want to like take the memory and inject it into this like vector. This is probably ending up using a memmove internally, which fucking sucks. So that means that we're gonna have to maybe get a little creative here. I wonder if you can like disable optimizations for a specific function. Or maybe what we do is we make a temporary thing. Instead of calling this function, we can maybe make our buffer manually. So we can say let vector or let copy is equal to vec with capacity n. This is an alloc vec. Then we can say this is a vector of maybe on init. Sorry, let's just include this. Use alloc vec. So this is a vec of maybe on init. So we need use core cell maybe mem maybe on it. Right. So this just tells the Rust compiler that we're like using uninitialized memory, and this is going to be of type U8. Have I spelled this wrong? Mabby, maybe not mabye. Then what we'll do is in an unsafe block, we'll write this loop manually. So we'll say for I in 0 to n, copy, I think it's I.write source.add I, something like this. And then we, what is this talking about? Consider copy.intermute.enumerate.takeN. No, fuck off. I just want a loop. Then here we say copy set len to n. I think this is the unsafe one. Unsafe function set len. Yeah, perfect. So now hopefully we've written, sorry, there we go. Hopefully we've written this in a way where it won't try to call memmove itself. That would be pretty unfortunate if this copy I.write was optimized into a memmove. So let's just kind of see where this goes. So we'll recompile. We'll file target release kernel to reload the debug symbols. We'll target remote localhost 1234 to connect to the new QEMU instance, and we'll hit continue. Okay. So here we've got like our hello logs. Very nice. And if I netcat, index is out of bounds. Oh, I'm an idiot. This will obviously crash because this is using like the normal vector indexing, which has bounds checking, but we know that we don't have bounds checking. So let's just say let copy pointer is equal to copy.as mute pointer, and we'll say copy pointer dot add I. Then we dereference it to get our maybe on init. We write it. There we go. So hopefully that bypasses the bullshit. Where did my window go here? And let's try this again. So we reload the symbol table, and we reconnect. Oopsies. Target remote localhost 124, and we continue. Fingers crossed, baby. Okay, so we've got like our hello logs. Very nice. We try to connect, and we say hello. Looking pretty good. Nice. Okay, hello. Yeah, that's pretty good. Let's go back to enabling the game. Since in release mode, it should be fast enough to run it. So let's go to main, and in game new, I guess it's in our game loop. We uncomment this self.update, and we set our delta back to 0.03 for 30 milliseconds. 33 milliseconds. That seems like a reasonable. I think that's like a standard time. I don't remember. We'll turn off GDB, run cargo release, and looking pretty good. So this is running. We're doing things in parallel. We're still using the TCP socket. Our game's still running while we do it. Yeah, that's pretty sick. So we'll say this is done at around 41:07. Now, I guess that means that we fixed our problem, which means that I have to think about what else I want to do today, because that was only 41 minutes, so we got plenty of time to do something else. Probably what I'll do is I'll start just going through the other uses of interrupt guards and stuff and trying to prepare for multi-core more. So let's do that. I'm happy with this. Well, I guess first let's clean up, right? We've kind of like left ourselves in a bit of a shitty state from all this debugging. So let's do that. We'll say clean up new sleep interval. Okay. So we'll kind of just commit randomly with a little smiley face. We're at async mutex now for it's safe, and then a bunch of smiley faces. So presumably this is an actual commit about async mutexes, and everything else after this is for the B tree or the sleep stuff. So we'll rebase a little bit. We'll fold these down, and we'll say we'll call this staging ground for thread safe sleep implementation. Okay. Cool. And now let's just look at what we've done. So our mutex stuff, this is just switching to atomics in the mutex. Great. All of this looks sane. This looks sane. Nothing crazy in there. So that's like a good isolated commit. Great. Probably in here, we are going to have a lot of shit to get rid of. Because we just kind of, we're like printing, we were changing shit left, right, center. So, one, we disabled our linter. Bad. So let's look at that. Here, let's uncomment this stuff. We've added GDB support, so that can probably be split into its own commit. So let's do this, actually. We'll see, git log. So we'll get checkout a branch for like rebasing. We'll reset this to the previous commit, and we'll get checkout everything. We'll like set the working directory to match that branch that we were just in. So b tree lookup, and we'll just reset our working directory to that. Great. And we'll unstage everything. And so now what I want to do is I want to like add the changes to the QEMU wrapper. So this is the GDB stuff. And we'll commit saying add GDB support to QEMU wrapper script. Great. That's one chunk of work. So we have these like wake up requesters being moved around. We have some serial stuff for the making serial writable or usable from within an interrupt without crashing. So maybe let's add that as its own commit. So this is some stuff in main and probably the stuff in serial. So let's look at that. Git add -p for the stuff in serial. So we wrapped this in an unsafe cell, and we allowed immutable references to write to the serial output. And then what else did we do? We had some stuff in main to use that. So not this, yes this. This is all related to the serial stuff. Great. some of this is, so we edit this patch, we say only take these changes, please. This is all not related to the serial stuff, not related to serial, not related to serial, not related to serial, not related to serial, not related to serial. That's probably it. So let's say, we'll say this is serial supports, support writing to serial from multiple immutable, from an interrupt without crashing, I guess. Now what I like to do sometimes is clear all the changes we've made and make sure that if I cargo run, everything still makes sense and works. Great, so those changes didn't break anything. We want to get back to the B-tree lockup state and discard changes that we didn't want. So now probably the ones that we want to take are the libc changes. And those are probably just all sane. So this is fix issue or fix infinite recursion in memmove. So this was, in some cases, memmove, the core library functions for slice vector manipulation were using memmove internally. This resulted in infinite recursion that only ended because of Stack Overflow breaking something else. Great. What else do we have? We have these linter changes, so fuck those. We have this like profile release having debug info. I'm okay with keeping that all the time for now. We'll probably maybe change that later, but we'll say enable debug symbols in release builds. I'm okay with that just being always on. What else do we have in here? Then everything else in here maybe looks related to the actual changes that we were trying to make the sleep stuff multi-thread safe. Yeah, we'll just do, so these are allocator logs that we don't actually want. And then this wake up list wake up requester, great. This was a very slight change that we don't want. Wake up list wake up requester, great, 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 great. All right, I think that's it. Very nice. Oh, this was annoying. This is something that I kind of... Oh, this one's fine. It was the one... Somewhere I had, like, a double await in there that was, like, really fucking ugly. You had this, like, async new. I don't like what I did there. Because I end up having this, like, future that I have to await to construct the future, and then await the future that it outputs. That's, like, kind of gross. But we'll leave it for now. Because I'm not sure that this is going to stay like this in the near future. I think that there's a good chance that once I refactor the future executor, that this will look different. So we'll just say support sleep from multiple CPU, from multiple threads. And to do better commit message. I don't really want to fill this in right now. Okay. Now we discard the rest of the changes, and we just make sure that we didn't lose anything important. So let's just compare this with what we had when we started rebasing. We've fixed the linter, we've deleted some useless logs that we didn't want, and we've removed like a superfluous? Is that how you say that? Superfluous.
Superfluous.
Yeah, a superfluous change. Okay. Great. So we're in a pretty good spot here. We'll say that this cleanup is done enough for now. And let's start just looking around at what to do next. So the thing that we're working towards is multi-CPUs. So let's fix stream title. So working towards multi-CPU support in my custom Rust OS. Great. show this back over here where you guys don't have to look at it. We'll change this to today's goal. We'll say this is today's goals and work towards multi-CPU. Great. So let's like just go into our code and maybe start looking at implementations of sync. So this is where like all the danger comes in, right? So the Rust's way of working is for things to be accessible for multiple threads, they need to implement this like sync trait, which I think is like a special trait that I couldn't really make up on my own. Sync. So test for which it is safe to share references between threads. So the idea is that maybe if I have a reference counted type that's not that doesn't use atomic count, then like that can't be shared between multiple threads because you need to have like extra memory barriers and shit to coordinate between those. And we've just kind of like ignored that for now and manually implemented this sync trait. So the idea is that like Rust won't let you, for instance, like put something in static memory if it's not sync, because that static memory is referenceable from all threads. And so either you need to like find a way to put something in that memory that's only accessible from one thread, like thread locals is like a good way to work around that. Or you need to like actually have atomic counts and stuff like that. So here we've just kind of said like there's a lot of places where we say like no, sync implementation assumes single threaded OS. And so we just need to like start working through those and get rid of them. Yeah. So let's think. So we have a sync implementation for InterruptGuard, and people are using InterruptGuards, but I wonder like who's actually relying on the sync implementation for an InterruptGuard, because the InterruptGuard does not guarantee sync anymore if we have multiple threads. So who relies on this? The interrupt service handlers, interrupt handler data. Sick. That's actually like basically nothing. So what we should do here is in our interrupts, okay, slowing down. When an interrupt happens, I guess maybe we'll start with what is an interrupt. So we have our CPU and he's executing code. Wah, 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 wah. These are like CPU instructions, and we're gonna be like here, and we're gonna have like our Ethernet card is gonna be over here. Maybe we'll draw the little Ethernet port. Boop, 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 boop. Looks kind of like somebody giving you the middle finger in a really shittily drawn cartoon. But this is supposed to be an Ethernet port, and maybe like some like data comes into the Ethernet port. We'll draw like a little box of some data, and he comes in here, and he's gonna say to the CPU like, "Holy shit! Something we got some data. Do something. I get it. Do something with it." And what happens is instead of like us going and like it's every once in a while going and looking at the Ethernet card, this is gonna like trigger an interrupt on the CPU. That's gonna say like basically every instruction when I move from here to here. Before like if this is like I'm like adding some numbers or something, he's gonna go like check and see if anybody's trying to interrupt him, and he'll go like, oh, time to run this other code over here. So he's gonna like in between this, he's gonna go over here, run some of this code that like does interrupt handler stuff, and then come back. And so what that kind of means is that since it's just like a raw jump over here, or not a raw jump, but it's not like a function call. It's like a special thing that's happened. You don't have like data that you had over here, right? Like usually you have like a reference to some data on your stack, but here your stack is like different. You have a new stack, and so what we do is we put like some like static memory over here that we say like, don't worry, you can always look over here for that. And so that's what like some of the stuff is. That's kind of like an oversimplification. There's another extra piece of info here where we've also registered an interrupt table with the CPU. So what happens is like this Ethernet card, he might say like, I am interrupt 4. And what'll happen is before we jump here, we'll actually go and look at like this table and we'll say like 4 goes to this. But you might have like a different interrupt handler for number 3, and so you might have like 3 over here. and he's going to jump here. And so we also have like this static chunk of memory where we like set up our function pointers to tell the CPU where to jump to. That's also in static memory. And we've kind of just used this interrupt guard as like an incorrect way of synchronizing this stuff. And so probably what we'll do is we'll just not stop doing that. So for instance, for this like interrupt service handler setup, we can, instead of making this interrupt guarded, we can make this an unsafe cell. That says, which basically tells Rust like, hey, we're gonna like modify data here sometimes, but we'll be careful, and we won't break your rules. And so here we say unsafe cell, new, great, and we'll probably do the same for this guy. Let's think about this. Yeah, so we can maybe assume the assumption we're gonna make here is that we only modify these one time on initialization of the system before interrupts are even enabled. So if we only modify these when interrupts are disabled, we can't have a data race where we're mutating this while somebody's looking at it, because the interrupt couldn't trigger. And so that's why we had this in like interrupt guarded before, but we're now kind of saying that how do I say this? We should only be able to have one writer of these guys. And let me think about this for a second. So how you might say that it makes more sense to like put a mutex on here as well and say that like you could have interrupt guarded mutex locked. You could like stack them and say that like we'll disable interrupts when we're working on these. And also if multiple threads try to modify them, we won't let them. But I think that I'm just going to take the hit and not deal with that type shit, because I know that we're only ever going to modify these during initialization, which is going to happen on a single thread. And if that later turns out to be untrue, then we can look at ourselves using unsafe code and be like, damn you should have done it better. Yeah, so that's what we're going to look at. So what are we doing? We're fixing interrupt handler sync code. Okay. Also, with these interrupt service handlers, I think that we're never going to change these after the first time. So yeah, it's like pretty safe to do this. So we'll use core cell, ref cell, and unsafe cell now. Great. This is saying that unsafe cell is not sync, which is fair. So we actually have to wrap this in another type. We'll say static struct ISRs, struct ISRs, and this is just going to be a small wrapper struct around this shit. And the reason we need to do this is because we need to be able to tell Rust that we're aware of what we're doing. So we're going to say unsafe impulse sync for ISRs. Maybe we'll make this like this. And then here we can say that this is now ISRs. I'm just going to put this comment. We're going to put this back in the right state so that we can compile the stuff that we haven't fixed yet. And here, this should be ISRs like this. Cool. Now we can look for this guy, and we'll just say on initialization, we say get. And we'll stick him in some unsafe. And we have to dereference him because he's a pointer now. And this is also a dot get. Like this. We need to throw a 0 on here when we use him. Makes sense. Because he's like the first element in this tuple now. And this should also just be an unsafe. Fuck it. We'll just make this whole section unsafe. Sure. Great. All right. All right. So if I cargo run now, we need to run release. Looks like everything's working, the fact that like anything is happening is a good indication that interrupts are still working as we expect, right? The interrupt service routines are getting called. Great. So we'll say get status, get diff, and we'll maybe lint. Oh shit. There's actually like my linter is probably in a really bad state right now because I forgot to format and clippy each of the intermediate commits. So we'll just cover that. I'll fix that later. Maybe I'll fix that now. It's kind of fun to show workflows sometimes. So we'll commit -m. What is this called? This is fixing ISRs no longer interrupt guarded. Great. Okay, so first let's fix everything. We'll call cargo format, cargo clippy, and we'll check out so we'll fix those. Sleep as in line 17, he doesn't want this. And in 105, usage of an arc that is not send or sync. What does that mean? The trait send is not implemented for mutex vectq, sure. Consider using RC instead or wrapping the inner type with a mutex. Okay, so here we just have to make our mutex type send for that debug to go away, for that log to go away, which I think is reasonable. We'll just do that. Cargo clippy, great. So we'll say add -u linter fixes. Okay, let's go back and fix up all of our lints for intermediate commits. So we'll just say that what did we do here? We said we made ISRs fixed ISRs syncness kinda, and so this was probably sometime before 102, and now we're working on cleaning up lints. Okay, so let's get rebase, or we check out a branch for reference. We check out rebase, and we just rebase -i origin master, and we just go and we at each of these points we edit our commit. And the idea is here now, if I run my linter, we're gonna have a bunch of problems. So we're going to cargo format, cargo clippy, and we're gonna lint. Great, no problems. So we'll add -u and git commit amend. So then we go one commit forward with a rebase continue. Let's check our status. So we lint. That's actually passing, so great. So we rebase continue. Once again, we've got problems, so we cargo format, cargo clippy, lint. Great, everyone's happy, it looks like. So we add -u, git commit amend, git rebase continue, lint. Great. Git rebase continue, lint. This is nice. I expected there to be more problems with this, but this rebase is going smoothly. Cargo format, cargo clippy. We need to make those same modifications we made before. So this sleep, we delete this thing here, and in our mutex, we implemented send, which was sane. Add -u, git and rebase continue, lint again, cargo format, cargo clippy, lint. Great, lint. I think that's the last one. Ooh, someone's not happy here. Why? Use create wake up list. Where am I? I'm in ISR is no longer interrupt guarded. What's happening? Why is this broken? Oh, probably because we never ran our tests in the sleep stuff. But shouldn't that have failed in the last iteration here? That's really weird. Cargo build. Cargo run. Yeah, that's very odd. What doesn't it like? What doesn't it like? Interesting. I don't really understand why anything would have changed here. Right? Because we didn't change anything related to where it's complaining. So there might be some sort of like caching bullshit. Yeah, that's very odd. So this is going to be a problem. But let's just fix this for now, and we'll fix this in a new commit, I guess, and figure out where that belongs later. So in TCP, he doesn't have a wake up list. He has a wake up requester. And can I construct that guy manually? Probably not. So here, instead of creating a wake up list from scratch, we'll just say let this thing is equal to, I think it's in create wake sleep construct wake up handlers. Yeah, this guy, great. And he has the first one is the one we want. Great. Cargo check test. That's one of the fixes. But in main 565, we have a problem here. So here we just probably need to like clone this or something. Let's see. This is a no. That's not it. Sleep move due to this call. Closure cannot be invoked more than once because it moves the variable wake up requester out of its environment. I don't understand why that's true. Oh, because it's an async move. Ugh. So we'll just say wake up list is equal to a reference to wake up list or something. I don't know. We'll see where this goes. Wake up requester is a reference to wake up requester. That doesn't like lifetimes, so we actually do just have to clone this every time. Okay. So now this should pass. Great. And I don't understand why this was passing lints before. Also, our tests aren't passing. What the fuck is going on? Interesting. That's odd. Very odd. Thinking. So this would have been related to the sleep stuff. Yeah, it's very strange. We'll commit -m smiley face. Oh, the wake up list stuff. If I remember correctly, didn't we have tests that were manually changing the time and checking resend and stuff? So those are probably the ones that aren't running. So can we see, maybe we look at what it's locking up on. So I think in our testing, we run each test case, and we print the name, and then we print the test case, and we say whether it failed or succeeded. And it looks like those might actually be all running. So let's just say print line all success. Okay, so it looks like we're hanging on exit. So here, it's probably, after we run our test, this sleep is probably causing problems. Which it is. So that's actually kind of interesting. So why would that be? It's because... Oh, it's because we changed this from a join to a select to a join. That's a mistake. This should be a select because our demo exits, but then we just never actually exit. And we changed that at some point because we thought that our OS was like... Oh no, that's not true. Sorry, I was confused. I was going to say that I thought that this is running forever and never exiting, but that's not true because we force quit the OS at this point, so that should be fine. So the problem is probably in this sleep. He's just never waking up, and so there's a bug in our sleep changes. That's kind of fun. That is kind of fun. So let's try to look at that actually. So we'll look at sleep, and we have this like service handler. So let's just kind of print line here, inserting time. And here, do we print in our wake up that we woke up? Maybe we'll say waking up at time. That's great. So let's run our cargo test. Nothing's happening. That's weird. Why the fuck not? Cargo run. Okay, so this is working. So why does cargo test not work? Oh, it is. Okay, so we are waking up, and let's look at the wake up times. We'll say, so why is he waking up over and over again if nobody's registering wake ups? Oh, oops, because we should only print here. So here, he's never triggering a wake up. Interesting. We also never register a sleep, as far as the logs are concerned. Unless I deleted that log. Oh, I'm just never... Oops, I thought I put a log here. What the hell? Registering wake up at... This is a tick here. Right, so he registers a wake up. And then in our service loop, here we never propagate the wake up. That's the problem. So here, maybe it's something to do with our demo feature. Ha! Yeah, it is. Fuck. Okay. So... fuck. So the problem here is that, how do we explain this? Maybe we need to draw it. Okay. So we have this like demo. And this is like runs our normal kernel and does like shows brick breaker, does like the TCP echo server, all of that. And inside here, he has the sleep service. And he's the one who propagates sleeps to like the interrupt handlers. And then we have like our testing. He bypasses this demo and doesn't run it. And so people are like requesting sleeps in this test infrastructure, and they're never getting run in the demo service, right? It's kind of like this or this, but not both. And so here, probably what I'll do is I just won't use sleeps. I think that's fine. Oh, it's not fine. Fuck. Okay, so the other problem is the test infrastructure that Rust provides us, that lets us like register tests with this like test main. This runs like a sync function, but our tests are async and might sleep in the test or something. I guess they might not, but they might. And so like if we require a sleep service to be running, it won't be running because our demo's not running. But I think maybe we can just say that people who are using sleeps require this to have to set up their sleep infrastructure themselves. And I think it's okay for me to just say in this. let start is equal to kernel monotonic time. Get, I think is what it's called. And we'll say let end is equal to kernel monotonic time get plus, or what's start, sorry, start plus kernel monotonic time dot tick frequency times, this is, start is ticks times ticks per second is going to give us 1 over second, or is going to give us second, or time squared. So we want actually, or frequency is ticks per second, yeah. So we want to do 1 over tick frequency to get seconds. So if we want to go do start is equal, the end time, if we want to sleep for like 0.1 seconds, is going to be start plus the time that I want over the tick frequency, right? So this is maybe like 0.1, and this is going to be here, and we're gonna say, we'll just busy loop. We'll say while kernel, oh, that's fucked. I actually can't do that. Then we need to make a future that we pull. So we say struct wait. Oh, fuck. I'm just reinventing sleeping here. Because I was going to say that we could just like busy loop for a second and wait for so that we give the logger time to print out the stuff it needs. But we do actually need to register ourselves with like the interrupt handler for sleeping, or else we won't propagate our sleeps, or we won't propagate our if we try to wait here and we like pull pending, we say like we're not ready yet, we need someone to schedule us, and that is the interrupt handler. But we might be able to like, we might be able to get around it by doing this here. We're gonna do some real hacky shit. We're gonna have a busy wait, and he's gonna store the end time, which is just a usize probably. And he's gonna also store the monotonic time, which is an RC monotonic time. And we're gonna say, we're gonna implement future for busy wait. And his output is nothing. And what we're going to do is we're going to say if self monotonic time get, is get not the right word? Get is less than end. We return poll pending, great. Else we return poll ready. But the hacky shit we're going to do here is here we're just going to wake up the executor. So we're basically banning the executor from taking a break. And we're saying every time you check if I'm ready, like I'm going to wake you the fuck back up. And so he's going to like hot loop, and he's going to like look, he's going to pull him and the logger over and over again until everybody's ready. Yeah, I think that's fine. And so, oopsies. Now here I can just say busy wait, and we can take in the monotonic time is the reference to the kernel monotonic time. And this is a RC clone. And then the end time is just end, and we await this. Great. And does that work? Cargo run. Runs the wrong thing. We want to cargo test. Right, so here this needs to be start as F32 plus this. Back to a usize, or yeah, usize I think is what we're using. Wake up executor isn't found here, so we just say future wicked executor. And we've misspelt monotonic time probably somewhere. Monotonic time. Great, and 588 is we wrote end here, but we meant self.end. Okay, so he boots, he runs a test, and he quits. Great, okay. So he quits, and we have these registering wake-ups. Okay, great. Let's remove these print lines that we added earlier to debug. Great, and get status, get diff, get add dash u, get comet dash m, sleep stuff. Okay. Am I done rebasing? Get rebase, continue. Okay, there we go. So what's in this one? This is more sleep fixing, so we'll get rebase dash I, origin master, and this goes to the sleep and multiple thread stuff. Merge tool. What tools do I have involved? What doesn't he like? Oh, this was a change in the here. So I guess we take B here probably because we hadn't changed the stuff yet. Get rebase, continue. Okay. And one more. We rebase from here, edit both these, and check the linter. Cargo format, get add dash u, lint. We're close. We have the wake up requester stuff. This is unused somewhere. Cargo lint again. What was the other thing that didn't like? Unused variable in main. 587. This should be underscored. Great. Lint. Hopefully everything passes. Great. We'll look at rechanged. And that's fine. So we amend. Get rebase. Continue. Lint again. Cargo format. Get lint again. Womp, 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 womp. All right. Thank God. I think we're almost there. Yeah, I think we are chilling. Okay. So I think that's pretty good. I guess we cleaned up our lints, and there was also some busy wait fix at some point. Okay. That's an hour 25. I think that's long enough that I don't really want to start a new thing now. I'm pretty happy with the B-tree fix, the B-tree set crash fixes. That was some. Basically, we made a poor assumption about what the kernel was or what the Rust standard library was going to be doing, and we fixed like several infinite recursions in there, as well as some crashes on printing in our interrupt handlers. We did some cleanup, did some rebasing. I think that like this git log is looking pretty fine now. We've got like a bunch of smaller commits that are easy to parse. I think that we've kind of wrapped up the saga of sleep from multiple threads from last stream, as well as we've kind of got a interrupt service handler routine registration no longer relies on the like sync implementation of InterruptGuard, which is like an untrue implementation. So all of that looking pretty good. Happy with what we accomplished. Yeah, if you liked what you saw, feel free to tune back in most days at like somewhere between 1 and 2 Pacific time. Just like to stream for a couple hours every day. And if you miss the stream but want to catch up on YouTube, there's a YouTube linked in the description. And if you're on YouTube and you want to pop by on Twitch and say hi, feel free. Yeah, thanks for watching. Catch you on the next one. Bye.